All right, so we're moving on in Chapter 3 today to 3.4. We're going to be looking at graphs of polynomial functions. And a few things to start with, just some keys to graphing that we're going to be working with. Checking for symmetry. Sometimes that is like concrete, like we do something physical, or we just observe the equation that we're working with that there's symmetry. Finding zeros and multiplicities. That's something we will do algebraically, always. The third one is to determine the end behavior, what's happening on the ends of the graphs. The fourth one is to plot additional points as needed. And you'll know when they're needed, because it will thus not be enough information to connect things otherwise. And the last one is to connect the dots with a smooth curve. So we're going to go through each of these kind of in detail next, but these are our 5 steps that we're going to use as we're graphing. So our first one is to take a look at symmetry. So sometimes symmetry is really obvious by the graph, especially if it's a very simple graph like the graph of x squared. You kind of know what it looks like. If you manipulate it just a little bit, like just adding a 5 on the end, it just shifts it up 5. You still got symmetry. But sometimes the symmetry is not quite so direct. So when it's not quite so direct, what we're testing for is that if a graph has y-axis symmetry, or it's even, then the x values, when we switch for the negative x values, yield the same y values. So f of positive x and f of negative x give me the same y values. Okay, and a key graph that you might keep in mind as you're thinking about this is just your basic graph of y equal x squared. If I put in all the, put in negative numbers for x or positive numbers for x, I get the same squared values. An odd graph has the case that when I put a negative in for x, it's actually giving me the opposite values for y. And a graph that we've seen that we've done this with and had this happen with before is x cubed. So if we put in positive 2, we get one thing. If we put in negative 2, we get the exact opposite sign. Okay, so those are our y-axis even or origin is odd. Those are the symmetry pieces that we will be testing for. We talked about multiplicity last time, so x-intercept behavior and multiplicities. So if c is a root of a polynomial with multiplicity k, if k is odd, the graph cuts through the graph cuts through the x-axis. And if k is even, it bounces off of the x-axis. Shake your head if you remember us talking about that last time. Okay, we didn't look at it from a graphical standpoint, but I mentioned it, that even and that odd did something different with the graph. So we're going to see those happening this time as well. So typically speaking, when we're doing things in step 2, we're factoring. We're having everything on one side set equal to 0 on the other side. We may be using synthetic division if that's appropriate, but we're doing something where we're breaking the polynomial down into its factors. End behavior. So this is something we have not talked about before. So I'll pause a little bit longer on this chart so that you can either take a picture of it or write it down if you would like. This actually talks about what happens on the edges of the graph. So as I go to the left and the right forever. So this is called the leading coefficient test. So we have 2 possibilities. We either have a possibility that the leading coefficient is odd or even, and then we have the possibility, I didn't say the leading coefficient, but the power of the exponent. And then the leading coefficient itself is either positive or negative. So if you have a graph that has an odd degree, right, the biggest exponent is odd, then what happens is that the 2 ends go different directions. So if the graph is odd, one end is going to point up and the other end is going to point down. And it will depend on whether or not your coefficient is positive or negative. So if your coefficient is positive, it goes up on the right and it goes down on the left. If your coefficient is negative, it goes down on the right and it goes up on the left. So it just flips. So negatives, we know they take a graph and they reflect it. So that's what's happening when I have a coefficient at the very beginning of my function that is negative versus positive. If graphs are even, you want to keep in mind things like your x squared graph, right, parabolas. Both ends point either up or both ends point down. If it's a positive, both ends point up. If it's a negative, both ends point down. So I'm just going to draw a real basic graph of each of these here. I mean, I've drawn at the edges, but something that would show up in those kind of categories, just so that you have a reference, kind of an equation. So this would look something like this, perhaps. Maybe it has more or fewer like peaks and valleys, but it looks something like that. And this one would flip upside down of that. And then on these bottom ones, we want to think parabola-like. They could, in fact, have other things. So I could draw it so that it has, right, like a W shape. That'll be fine. It's the edges that I care about in this discussion. And on the edges, they point down. So these are the kinds of graphs that come out of end behavior pieces. Now you might notice that we've talked about steps 1, 2, and 3. Step 4 is to plot additional points, and step 5 is to graph smoothly. Those aren't things that we have to do any pieces with in terms of formalized description. They're actually more like action steps of what we're going to do. So we don't have to list them out in any specific way. We're actually going to get started on doing some examples. So if we take a look at this particular graph, or this equation, x cubed minus x squared minus x plus 1. And we're going to run through the different pieces of information. So we're going to start with symmetry. So notice if I put in positives or negatives, we'll talk about what happens when I put in negatives. Some of the signs will change, right? Like if I put in a negative into x cubed, it'll stay negative, right? But if I put in a negative to x squared, it's going to stay positive. So some of them are going to stay the same, some of them are going to change. And in order for it to be either even or odd, either everything has to change to be positive, or nothing should. Everything should stay negative if you've put in negative. Well, I don't have that happening on this function. Right, if I actually wrote this down, this one will stay negative. Whoops, I meant that to be a highlighter. Let's try it again. This one will stay negative. This one will stay negative. This one in the middle, its sign changes, right? I mean, it says negative x, and then when I square, it's going to give me a positive. This one stays negative. So some of them are doing one thing, and others are doing the other pieces. In particular, if I actually simplified this out, this would end up being a negative x cubed. This is positive x cubed, but then there's a negative in front, so this would be negative x squared. These are two negatives, so I would get a positive x, and then I'd have a negative one on the end. And if I compare that back to what I have right here, they didn't all change signs, and they didn't all stay the same. And so when that happens, it's neither in terms of symmetry. There is not y-axis symmetry, and there is not origin symmetry. There's no symmetry. So you can either say neither, or you can say no symmetry. There's nothing going on that helps us out in terms of symmetry here. My second step is to set things equal to 0. So we have x cubed minus x squared minus x plus 1 equals 0. And it is 4 terms, so factoring by grouping is a good place to start if it will work, and often it will. So if I group these two pieces together, what do x cubed and x squared have in common? X squared. And if I take out x squared, what am I left with? Wonderful. Now the second piece, negative x and positive 1 don't have anything in common. I mean, they really don't. But their signs are opposite what the sign is inside of here, right? The x is negative, the 1 is positive, and I really want my x to be positive and my 1 to be negative. So in order to make this work, I'm going to need to factor out a negative 1 so that I can get the signs to switch. So now I have a positive x and a negative 1. We've done that a few times. Make sense? Cool. And then, which is what we wanted, our parenthesis parts are the same. So I can pull out x minus 1. The parts that remain multiplied on the outside are x squared minus 1, like so, equals 0. But x squared minus 1 factors. How does it factor? Right. It's a difference of squares. It's x minus 1 and x plus 1. That was a specialized formula that we looked at a little bit back. And you'll notice now that I have two x minus 1 factors, right? So this is x minus 1 squared and x plus 1. So that's my complete, condensed factored form. And then if I take each of the pieces, the squared is irrelevant in terms of setting it equal to 0. So I set each of the pieces equal to 0. If x minus 1 equals 0, what does x equal? 1. And if x plus 1 is equal to 0, what does x equal? Negative 1. And this is where what we did last time comes into play. This one has a multiplicity of 2 because it has a power of 2, okay? This one has a multiplicity of 1 because I don't see anything here, so it's an understood power of 1. So both of those pieces of information are very helpful. In terms of my graph, part A did nothing for me. I don't have any symmetry, I don't have any useful information out of it, but part B, or this part number 2 or whatever, actually gives me the x-intercepts. So it crosses the x-axis at -1 and +1. Right? It hits the y-axis at those points. One more piece of information before I can actually connect those and see how they're going to connect. Number 3 is the end behavior. End behavior. What is the highest degree, or what is the degree of this polynomial? 3. So the highest exponent, the degree of this polynomial is of 3. Which means as I'm looking at this chart, I'm in the odd category because 3 is odd. So the graph will either point like this, up on the right, down on the left, or like this, up on the left, down on the right. And we determine it based upon the x, or by the coefficient in front of that leading term's exponent, where the exponent was. This coefficient's a number 1. In particular, that's a positive coefficient, right? So looking at this chart, if I have a positive exponent, I didn't say that right, a positive coefficient with an odd exponent, I'm in the top left-hand corner. I'm right here in terms of my location, right? It's going to go up on the right and down on the left. So you can just draw that in if you wish. You can write that out if you wish. Down left, up right. I don't care how you notate it, but it needs to be something written form to remind you what's going to happen. It actually gives you quite a bit of information to be able to fill in something in between here. So over here, this has to go up. And over here, this has to go down. Now, it doesn't tell me what happens in between, but I know the ends have to do that. Is that good for everybody? Okay. The multiplicities now. Let's go back and actually capture what that told us. At x equal 1, it has a multiplicity of 2. So over here, I should be bouncing off of my graph. If my multiplicity is even, that's 2, it bounces off the graph. So over here, it won't cut through. It's not going to do that. It's going to bounce back up. And then at -1, the multiplicity is odd. So at -1, it has to actually cut through the graph. So it's got to go like this. And clearly, somewhere in between here, these two ends that are now pointing upward, or like in the top half of my graph, have to connect. And that additional points that we plot would be helpful. In particular, when it talks about x-intercept behavior, it's often useful to find y-intercepts as well. So that can be one of the additional points that we do on number 4, if it's necessary. I can let x equal 0 and figure out what y is. So if x is equal to 0 in this equation, what will y be? It'll be 1. So 0, 1 would be an additional point I could plot, like so. And if I connect the two yellow dots that I originally had with the yellow dot that I just created, it would look something like that. So I realize that many of you, though not all, do have graphing calculators, and you are more than welcome to double check and make sure that the graph seems reasonable by your calculator. However, if all I see on your work is just the graph, it means you didn't do any of the work by hand, then you're going to lose lots of points and you're going to be very sad. Because you're going to feel like, dude, I got the graph, where's the rest of the stuff? Well, I didn't ask you to just do everything in your calculator. I want to know how you think about graphing, not how your calculator thinks about it. So do make sure that you're listing out all these pieces as you're finding them before you go utilizing your calculator to confirm. Any questions on this graph? Okay, let's try another one. Different equation. Negative x to the fourth plus x squared plus 12. And we always are going to start with symmetry. Not because it really matters which one we start with, but we've got a list of things. That's the first one I listed, symmetry. So if I were to change every x value and put negative x in on this one, there's a negative here, then it's negative x to the fourth, and it's plus negative x squared plus 12. What is negative x to the fourth? It's x to the fourth, right? It's even. So since this is even right here, when I multiply an even number of negatives, it becomes positive. And there's still a negative out here in front. So the negative out in front stays, but the negative x to the fourth inside here becomes just x to the fourth. What about my negative x squared? It's also going to stay the same, right? It's going to become positive. So I've got the positive that's in front right here, and then the negative x squared is a x squared, and my positive 12 at the end. How does that compare to my original equation? It's exactly the same, right? This is equal exactly to the same g of x I started with. So if you take a look over here, one more back, that's an example of the very first one. When I put the negative x in, right, it equaled exactly the same thing as I started with. So this graph is even, or it has y-axis symmetry. You can write either one of those things down. I'll write both for the moment. So I don't sketch this, but maybe it looks something like this. It folds over in half. But maybe it has more interesting features like that, right? Where it still folds over in half, but we've got like a W shape or something going on. But we need to see, does it cross, well, that was not going to work. Something like that. Does it cross the x-axis any? Or does it cross the y-axis? So we have lots of things, but whatever happens, whatever's on the left-hand side of the y-axis will mirror whatever's on the right-hand side of the y-axis. That's what this is telling us. My second thing is to let negative x to the fourth plus x squared plus 12 equal to 0. So is that negative in front of the x to the fourth? Yeah, that's really annoying. It's very difficult to factor when you have a negative in front of your leading coefficient. So instead of trying to do so, you can do one of two things. You can either factor it out in front so that it does like this, negative x to the fourth, it changes all my signs, negative x squared and minus 12 equals 0. You can do that. Or you can divide it out. So simply divide everything by a negative. Okay, it doesn't make any difference because it's a number. You're allowed to do that with numerical values. So I'm going to just do it that way since that's the second one I drew and I don't want to erase anything. Either way, we're going to be attempting to factor the same thing, the x squared minus, x to the fourth minus x squared minus 12. Now I recognize that's not exactly a quadratic, but it is very similar to a quadratic. It has a quadratic form. I've got a power 4, I've got half that power, a power 2, and then I've got a constant. They don't all have anything else in common, but the x to the fourth can be broken apart as x squared, and we can use trial and error. I need two numbers that give me a negative 12 when multiplied, and when they add, they give me a negative 1. 3 and 4, which one should be negative, Kylie? So one has to be negative. The 4, you're right. And why? Well, the 4 has to be negative because we have a negative x squared here. So when I look at my inner positive 3 and my outer negative 4 terms, they've got to add to negative 1, not positive 1. All right, so we can do one more piece of direct factoring as it's written. We can factor the x squared minus 4. How will that factor? Yep, x plus 2, x minus 2. Okay, is that good? What's that? Actually, you can't quite, at least not over the real numbers. What did you have in mind? But it doesn't work because it's a positive between instead of a negative. If there were a negative between it, we could, like if it said x squared minus 3, but it still wouldn't be 3s. It would be square root of 3s, which makes it a little messier. But you could do it if you had that, yes. The fact that it's x squared plus 3 actually means that that piece would actually give me imaginary solutions if I tried to factor or solve it. So this piece is not going to show up on a graph. So it's not going to affect the graph, I should say it that way, in terms of how it's drawn. The other two pieces, though, I can set equal to 0, and they will affect the graph. So if x plus 2 is equal to 0, what's x? Negative 2. And if x minus 2 is equal to 0, what's x? Positive 2. And what are the multiplicities on those? They're both 1. I don't have any exponents here, so they're understood exponents of 1. So both of these have multiplicities of 1. In other words, the graph cuts through at negative 2 and at positive 2. And we can draw that on the graph. So here we have our two dots. It will either go through like this, or it'll go through like this, right? And the reason I know that they will both do the same thing is because it's got to be symmetric. Make sense? There's symmetry involved. The left-hand side, the right-hand side have to do the same thing. In other words, I can't do this because then it's not mirror images, all right? Now, I do need to figure out which one it is. Is it both going up or is it both going down? And that's step 3. So step 3 is, I'll put it up here, the end behavior. So the end behavior is the degree. So what is the highest degree? 4, which is even, right? Telling you that they both point up or they both point down, which we already knew from symmetry, so that's good that that confirms. And then the coefficient in front is negative, so how will the graph point? They will both point down. So down on both sides. So the graph cuts down like this on the left and down like this on the right. But we need to fill in what happens in between. And much like we talked about on the previous problem, because the y-axis is actually happening in between, it might be good for us to find my y-intercept. Does that make sense? So my additional point that we would need between, if I let x equal to 0, well, I'll do it here. What's y going to be? 12 is right, yeah. If x is 0 in that equation, y would be 12. So my graph will cross up here at 12. And I might need to redraw this in a nicer way. So I'm going to cut this out so that it makes it a little bit steeper. It's a very narrow looking graph, right? And the graph will look something like this. The multiplicities tell us I don't want to redraw. The multiplicities tell us that it cuts through. If the multiplicities are odd, they cut through the graph, which ours were. They were both 1. If the multiplicities are even, they look like this, where they bounce off the graph. So they do not cut clean through and go from above to below or below to above. Okay, what do we think? It's okay?
Why does it look like a parabola and not like the little end thing that's on the table?
So that's a good question. If I have more details, if when I plot more points, I might find that it does have something where it has other shape around it. We're not worrying too much details about that. This is a sketch. It has the features we're looking for, namely it's symmetric, I have the right intercepts, I have the right end behavior. So as you look at your calculator, and I don't know because I don't have this one drawn from a calculator's perspective, it might actually look a little bit different for a sketch in the calculator. Let me just check and see what mine looks like. Did you look at yours, Kylie?
No, I didn't even think about it. I was just asking. I didn't know.
No worries. Yeah, it is the same. It's really flat on the top of it, if you look at it in your calculator. But it does look like this. What this doesn't tell me is that like the information that I've done so far is it has this form in between the -1 or -2 and +2. I know that y-intercept's there, but in theory, it could be looking something like this. I'll draw you a sketch. So here's these values that I know connects them. It could actually be doing something like this without me knowing it, right? Like the McDonald's arches going on. It's possible. But we're not trying to get super detailed enough information as that because we don't have all the tools we would need to be able to ascertain all those pieces. But that is possible. Okay, let's look at the next one. I think I have 2 more of these. Okay. Oh, how nice. What's so nice about this one in some ways? It's already factored. So that's going to help us out on step 2, because step 2 is about factoring. Not going to help us out so much on step 1. Step 1 about symmetry, this is not so friendly that this is all written out. But we can determine that we have some things failing for it to have the symmetries. Let's come back to step 1 in just a second, because when we do step 2, I think you'll see why it fails on step 1 pretty quickly. What's not very helpful on step 1 here is to actually replace all the x's with negative x's. Because then you have to decide again, did it change things, did it not change things? And it's not directly obvious on this one because of the form that it's given to us in. But if we look at step 2, it will be obvious to us very quickly. So this is my step 2. I set the equation equal to 0. And like we said, it's so nice because it's already in factored form. So if I set each part equal to 0, this is x equal to 0. X plus 6 equal to 0, and x minus 7 equal to 0. So this one's already done. What's its multiplicity? 1. What is x equal if x plus 6 equals 0? -6. Multiplicity 2. Remember, it's the exponent here that we're looking at. How about x minus 7? What does x equal? 7, thank you. And what's its multiplicity? 3. Okay, so far so good? Let's plot those points. So I'm supposed to hit the x-axis at 0, at -6, and at +7. So I contend that information enough tells me that this is neither. So let's go through each of them. Why does it not have y-axis symmetry? Because on the left-hand side I hit at -6 and on the right-hand side I hit at +7. They're not hitting the x-axis at the same location, right? So it fails to have y-axis symmetry. Origin symmetry means that I can spin it around like a spinner so that everything on the left-hand side spins to the right-hand side 180 degrees, and it fails for exactly the same reason, right? The -6 on the left would spin to +6 on the right, not to +7. The positive 7 on the left would spin to negative 7 on the left. Positive 7 on the right would spin to negative 7 on the left, not to negative 6. So it doesn't have that origin symmetry either. So it does not have any helpful symmetry. Does everybody see that okay? So my left-hand side of this graph, my right-hand side of this graph are not going to look the same. The fact that I do have multiplicities that are even and odd are interesting on this one. Odd means that it cuts through the graph. So it's going to cut through at 0, and it's going to cut through at 7. And at 6, it's going to bounce. So we'll come back to the bouncing or the cutting through right now. The reason I don't want to deal with it yet is because cut through could look like that, or cut through could look like that. I know number 6 doesn't have a cut through, but you know what I'm saying? Like, I don't know which one it is so far. So let's do a little bit more work before we draw those pieces in. The end behavior will help us out. All right, what is the overall degree of this? Because it's not multiplied out. Can you tell? I've heard 5 and I've heard 7. It's neither one of those. What do you think, David? You were thinking 5? It's 6. Who says 6? Okay, can somebody tell me why you think it's 6? It is 6. You want to do it, Tiffany? Why do you think?
Calculation is not really mathematical. 3 and 2, that's going to give you a power of 5, plus the x being outside is going to be 3.
That's exactly why. So there's an x to the 1 out here. When I FOIL this out, I'm going to get an x squared. When I FOIL this, or distribute this out, I'm going to get an x cubed. And when I have x times x squared times x cubed, I'm going to get an x to the 6th. There will be an x to the 6th if I multiply this out. Okay? So my degree is even. So that tells me that both ends either point up or both ends point down. Can you tell me what my leading coefficient might be based on the graph or the equation that's given? Somebody be bold. What do you think it might be? You're right, David. It's 1. Do you know why? You're right. None of those x's have a coefficient. Do you see that? So as I'm distributing and I'm multiplying things out, I'm going to be multiplying x's by x's, but I'm not going to be multiplying x's by 3 x's, right? Not for the highest degree term. Each of these has a coefficient of 1, 1, and 1, and they're all positive. So I do get a coefficient, a leading coefficient of positive 1. So my leading coefficient is positive. So the degrees, being both the same, means I need to point up or both point down. Which one will this do? Up, because it's a positive. So I will point up on the left, up on the right. I'm pointing up on both. So that tells me my edges both go upwards, like this. I just need to fill out the pieces in between. And this one's actually fairly nice because I already have the y-intercept plotted, don't I? Happens to be the origin on this one, so I don't have to plot an additional point here to make this work. Okay, so we're going to read the graph from left to right. The first x-intercept that we come to is negative 6. Am I supposed to bounce or am I supposed to cut through at negative 6? I am supposed to bounce, which means it's going to look like this. And it's going to go up for a little while, and then it has to come back down because it has to cross back at the origin. You might be asking, well, how far do I know how it bounces? Well, if you want to be more precise, your best guess is to choose the value that's halfway between and test it. Okay, well, let's just check 3. Sorry, negative 3. Right? The x value of negative 3 should tell me. So if you put in negative 3 and you figure out what it is, you're going to get a value here, and that will give you a point to plot. You don't have to do that. But if you want to have a little bit more precision, you certainly could. But halfway in between at 3, wherever I am, it's going to stop going up and it's going to have to come back down. So you see happening here is that it's got a peak happening there at negative 3, right? Okay. What happens at x equals 0? Does it cut through or does it bounce off? It's going to cut through. And again, it's going to go down for a while, and then it has to come back up, and it has to hit my last point at x equal to 7. It will go for it for about halfway, and then it'll come back up. So at about 3.5, it will have its minimum, and then it will come back up. Is it really deep like that, or is it really shallow? I don't know, because I didn't actually get that point in between. It doesn't really matter. We're looking at the overall shape. This is the overall shape of my graph, either way. Say again? We didn't end up needing to. You could plot some additional points if you wanted a bit more accuracy in your graph. Do I want to know how far up and down it goes on those bounces? We could, but we don't have to get the overall shape on this one. Any questions on that one? Okay, we have one more. This question's a little bit different. What's different about this problem than the ones we've been working with? What's it say? It's an inequality. This says greater than 0. And in fact, it says greater than 0. It doesn't even say y equals, right? Or g of x or k of x or f of x or whatever. It doesn't have any of that in it. It just has an inequality symbol and a 0 in it. So we talked about, I can't remember if it was last time, I think it was last class period, we talked about a test point method for deciding on inequalities. And we set things equal to 0 and put them on a number line, and we tested points in between. Shake your head if that sounds like something you've heard recently from me. Good. This is actually another method, and it's using graphing. Now, we've seen this equation before. Out to the side of this, it says example number 1, right? I should look back at number 1. So number 1's example was this graph, and it was the same equation, but it said f of x does not say greater than or equal to 0. Right? So this is the same thing that I have on number 4. Okay, everybody good so far? And when we did that, we created this graph. So I'm going to take this graph and I'm going to copy it and paste it and put it on the other slide, because that graph is how we're going to answer the question this time instead of using test points. So I want to show you how that works. Where's my axis? Didn't have that copy pastable height. Okay, that's pretty close, I think, to what we had. Does that look okay to you guys? Okay, this says that I want it to be greater than 0. Okay, the 0 here is representing the function values, right? F of x or y. In other words, I want my y values to be greater than 0. So on a graph, where are y values positive? On the top. So the answer is going to be whatever the values are where they are on the top. So if you take a look, this part is all on the top. Right? Everything I just kind of highlighted in yellow, except for the point where it actually hit the y-axis, which was over there, I think, at 1. Is that true? This is at 1 and this is at -1. So this location, it actually equals 0 because it hits the x-axis, but both before it and after it is above the x-axis. So this graph from -1 all the way to +1, I'm above the x-axis. Briefly, at +1, I'm on the x-axis, so I don't get to include it. And I don't get to include the -1 either because I'm on the x-axis. But then from 1 and on, so 1 to infinity, I'm also above the x-axis. So what we had done before is we'd done test points. So we had created, we set things equal to 0 like we did on problem number 1. We found this -1, we found this +1, and we tested points in between. And so we would have tested a 0 and we would have got a positive here, and we would have tested like maybe a 2 and we would have gotten a positive here, and we would have tested maybe -2 and we would have gotten negative here. And we would have found out that these things were our answers, just like we did with the graph. We just did it with a numerical form instead of a graphical image. So this is using a graph to verify the same thing that our table did before with our sign table. Okay? Any questions on that? So generally speaking, if you were given this problem, wow, I don't know why that's so thick. Let's try that again. If you were given this problem from the get-go, it wouldn't be already solved for you, right? Like we did on problem number 1. What would you have to do? Well, you'd have to do the same things we did on problem number 1. You'd have to factor it, set things equal to 0. You'd have to graph it with all the pieces, and then you'd use the graph to determine where it's above the x-axis or below the x-axis. This one was above because it said greater than 0. If it said less than 0, we'd be looking below. If it had equals to, we would include the x-intercepts. Any questions on that one? All right.